This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will start by discussing the application scenario of binary search trees, or say where binary search trees can be useful. After that, we will introduce you to binary search tree and cover one of its basic operations, the search method. As we do that, we will also conduct a time complexity analysis on this method. Let's get started. So, when binary search trees can be useful. First, binary search trees support searching when you have a dynamic data. When your data grows or shrinks a lot, a binary search tree can also do that without needing to reallocate those memories. In contrast, the sorting algorithm relying on using arrays for data storage cannot do that, like a heap or merge sort. Second, a binary search tree can support many tasks that are relevant but beyond just searching. A binary search tree allows you to perform range queries or successor or predecessor lookups. It allows you to efficiently find the next greater or smaller element, or retrieves elements within a range. Due to its efficiency and versatility, binary search trees have many applications in real world. For example, our internet. Domain name system lookups uses binary search trees for fast searching of domain names. The domain name system is like a phone book of the internet. It helps translate human-readable website names to IP addresses, like this one. So computers can find the IP addresses given a domain name. This process needs to be very fast because every time when you visit a website, your device performs a DNS lookup, and there are millions of people like you. That's where binary search trees shine. Okay, knowing where binary search trees can be useful, let's start exploring what they are. A binary search tree is a binary tree in its core. Just in case if you don't know enough about binary trees, a binary tree is a data structure where each node has at most two children, called the left child and the right child. It starts with a root node, and each node can have no more than two nodes branching from it, forming a tree-like structure. A binary search tree is a binary tree with a special feature. In a binary search tree, the left subtree of a node contains only nodes with smaller values. The right subtree of a node contains only nodes with bigger values. An example of binary search tree may look like this. You can focus your attention on any nodes, and then check its left or right subtrees to examine this special feature, or say property of binary search trees. For example, if you focus your attention on the root node with a value of 50, all the nodes in its left subtrees are smaller than 50, and all the nodes in its right subtree are bigger. For another example, you can focus your attention on the node with a value of 66, right here. Its left subtree only contains nodes that are smaller than 66, and its right subtree only contains nodes that are bigger. Just to be sure, a binary search tree doesn't contain duplicates, or say nodes with the same values. We will assume that every node is unique, or say the values of all nodes are different. Now you know what a binary search tree is. Let's talk about its implementation. Before you ever think about implementing a binary search tree, its basic unit, a binary search tree node, needs to be implemented first. The implementation of a binary search tree node bears a lot of similarities as a linked list node. They both can store some values in a node, and both store some references pointing to other nodes. However, in contrast to a linked list node, a binary search tree node has two references to its left and right children. Based on the definition of the node class, we can move to structure the binary search tree class. In the class representing a binary search tree, short for BST, we will start by declaring a node that represents the root node of the whole tree structure. In the class representing a binary search tree, short for BST, we will start by declaring a node that represents the root node of the whole tree structure. This will be the entry point to accessing other nodes in this tree. Beyond that, we will define a set of functions representing the basic operations required by a binary search tree, including search, insert, and delete methods. These methods need to be implemented one after another as functions. With the binary search tree skeleton set up, our next task is to implement the search function. As the name indicates, the search function, or the search method, aims at searching for a given value, a target value. It certainly involves a few steps. Let's start by assuming that we have a binary search tree that has been defined and declared with many data points, like this one. To perform a search task on this given binary search tree, you need to start accessing its data first. So the first step is to access the root, and that's the entry point to any other nodes in this binary search tree. Second, you will compare the target value to that of the current node. If they are the same, then great, the job is done, the target is found. So you would simply return true in that case. If the target value is smaller than that of the current node, you will move to search in its left subtree. Remember, this is a binary search tree. All nodes in the right subtrees are bigger than the current node, so there's no point in comparing them to the target anymore. Similarly, if the target is bigger, you will only need to search in its right subtree next. In the end, if you reach a leaf node, yet still can't find a node with the same value as the target, it means that no other nodes have the target value. As a result, it will return false. Let's go through an example to further make sense of these different steps. For example, you are given a target value of 36 to search for in this binary search tree. Your starting point is the root node. 36 is smaller than the value of the root node, so you continue your search in its left subtree. You can safely ignore its right subtree because all the values in the right subtree are even bigger than the root node value. Next, we will compare the target 36 to the node of 31. The target 36 is bigger than 31, so you can continue your search in its right subtree, like this. Now you compare the target 36 to the node of 41. The target 36 is smaller, so you continue the search in the left subtree of node 41, like this. Now, you compare the target 36 to the node 32. The target is bigger, so you continue the search in its right subtree, like this. The target is still bigger, bigger than the node of 34, so you continue the search in its right subtree, like this. Now, you are at the node of 36, which has the same value as the target. After comparison, you will return true, and the job is done here. If you reach a leaf node, yet still can't find the node with the same value as the target, it's guaranteed that you can't find such a node elsewhere in the binary search tree. In such a case, you would return false instead. Now you know how the steps work based on this example. Let's convert it to the pseudocode. Here, we are doing some overloading methods in the pseudocode. The same function name, but with different parameters. The first function, this one, is the one that is exposed to the users. The second function is hidden from the user, but does the heavy lifting behind the scene. It doesn't have to be set up like this, but this setup makes the recursion easier. The first function is more like a wrapper that's exposed to the users, and the second function does the actual work. So let's focus our attention on the second function. This function takes two parameters, the target value and the current node. In its base case, it either returns true or false. It returns true when the target is found. It returns false when you go beyond the leaf node. How do you tell that you are beyond the leaf node? When your node becomes null. In that case, you return false. Well, the pseudocode is not a direct line-by-line translation of the steps we just described. The base case here is a combination of the case A in step 2 and step 3, like this. When the target is either smaller than or bigger than the target, you continue the comparison via the recursion. When the target is smaller, you run the search on the left subtree of the current node and return the search result. When the target is bigger, you run the search on the right subtree of the current node and return the search result. That's everything about how the search function is implemented. Let's discuss its time complexity. We will start with the worst case first. So what does the worst case scenario look like for the search function? Or say, what kind of binary search tree in a target value will lead to a worst case? Before picturing such a tree structure, we can at least say that the worst case will force you to compare every node in the tree to the given target value, literally every node. Knowing that, it's not so hard to find such an example. When you have a binary search tree that looks like a singly linked list, and the target to search for is the node sitting at the very tail, you have a worst case. An example can be the one that sits on your left. Technically speaking, a singly linked list can be a binary search tree, as long as the property of the binary search tree is maintained. In this example, every node happens to have only the right subtree, and each node is bigger than its parent, and the target to search for is equal to the value of the last node. For another example, you may have a binary search tree looking like this, still a singly linked list, but the nodes are not in the perfect ascending or descending order, and the given target cannot be found in this tree. However, as long as every node needs to be compared to the target in the search process, you will have a worst case. Assuming that a binary search tree has a total node number as n. In the worst case, every node is compared to the target in the search process, and every comparison takes constant time. So the time complexity of the worst case is linear time, expressed as Tn belongs to big O of n. What about the best case? The best case is somewhat trivial in comparison. Given a binary search tree like this example on our left, if the target value is the same as that of the root node, like this, you will have a best case, regardless of how big or small the binary search tree is. As long as the given target is equal to the value of that of the root node, you have a best case. In the best case, you only need to perform one comparison before the job is done. And such a comparison takes constant time. So the time complexity will be constant time, expressed as Tn belongs to big O of 1. What about the average case? It's certainly trickier than that of the best and worst cases. We need to use the help from the expected value to account for randomness. We need to make sure we are on the same page before we can start computing the average case, such as the assumptions we have, the choice of the random variable, and the probability. Let's start with the assumption. We would assume that the binary search tree is randomly constructed and relatively well-balanced. By saying that, I mean you don't have a left or right subtree that is significantly bigger than its counterpart. If the binary search tree has n nodes, with this assumption, we can safely say that the height of the tree is roughly log n. With this assumption set, we have two different scenarios to explore. The first scenario is unsuccessful search. For an unsuccessful search, we don't need the help from the expected number because unsuccessful search always ends up with checking the last node at the leaf level. Remember our assumption. There are n nodes in total in a binary search tree, and the tree is well-balanced, so the height of the tree is log n. Each unsuccessful search takes the same number of comparisons as the height of the tree. The time complexity is in proportion to the total number of comparisons, considering each comparison only takes constant number of steps, or say constant time to run. As a result, under this scenario of unsuccessful search, the time complexity is log n. That's the first scenario. The other scenario is successful search, which requires the help from the expected number. In other words, for this scenario, we need to identify the proper random variable and the corresponding probability. Same as the unsuccessful search, we will be estimating the number of comparisons instead of the actual time complexity because the two are in proportion to each other. Focusing on the expected number of comparisons saves us from the triviality of counting steps in time complexity analysis. But different from a successful search, we will try to establish a recurrence relation on the expected comparison number before we ever attempt the formula of its complexity. We will pick the random variable as the number of nodes in the left subtree of the root and use letter I to denote it. Given this random variable I and the total number of nodes as n in a binary search tree, we will be able to deduce that the right subtree of the root contains n minus I minus 1 nodes, and 1 represents the root node. If the total number of nodes in a tree is n, the chance of each node being compared to the target is critical to none. Since the tree is randomly constructed, all the values are arbitrary, so each node has an equal chance to be compared to the target. That said, the chance, or say the probability, is 1 divided by n. This is not the probability of our random variable, but a super important piece of assumption. Based on this assumption, we can deduce that after comparing the target to the root, the chance it goes into the left subtree is I divided by n, because there are I nodes in the left subtree. In other words, the chance of the target being compared to nodes in the left subtree is I divided by n. Based on that, we can also deduce that the chance of the target being compared to nodes in the right subtree is n minus I minus 1, then divided by n. Now we have everything we need to compute the expected number of comparisons, or say the recurrence relation for the expected number of comparisons. This recurrence relation can be expressed as the following. In this formula, Cn represents the expected number of comparisons at the root, at the right side of the equation. 1 represents a single comparison between the root node and the target. This summation item represents the expected number of comparisons in the next step. This is an expected value, and that's why it is a sum of 2 items, and each item is a product between the random variable and its corresponding probability. I divided by n multiplied by c of I represents the expected number of comparisons when the search goes into the left subtree, while the other item represents the expected number of comparisons when the search goes into the right subtree. With the recurrence relation set, we can start deducing the actual formula of Cn that's independent of the random variable. First, we will use our assumption to simplify the formula. The assumption that the binary search tree is fairly balanced, which means that the left subtree and the right subtree have about the same size. Based on that, we can eliminate the expected comparison number of the right subtree and multiply the summation item by 2. Second, we will use the continuous approximation of the expected value over all possible subtree size to replace the summation item. After that, we can use the differential equation form and integrating both sides to get a formula like this. Third, when you exponentiate both sides of that formula, you will be able to estimate Cn to the natural logarithmic of n. It's worth noting that the natural log of n grows at the same rate as log base 2 of n, although it may not be so obvious to tell when you plot them on a 2D plane. You should trust the math formula. Natural log of n can be expressed as log base 2 of n multiplied by another constant number. In other words, the two are asymptotically equivalent. That's why we can use log base 2 of n to replace the natural log of n to estimate Cn. Based on that, We can conclude that the time complexity grows at the rate of log n, expressed as Tn belongs to big O of log n, regardless of whether the search is successful or not. Tn, the time complexity, grows at the rate of log n in the average case. Now you understand what a binary search tree looks like, where it can be useful, and one of its basic operations, the search function. In the next video, we'll dive into another basic operations of binary search tree, which is the insert function.